I'm essentially describing a simple cosmological model with equal velocities of radiation and expansion in 4 space dimensions plus time. It's fairly different to the standard model. Among other things, it has a constant wave-like velocity of expansion at the speed of light, which has a number of surprising implications, some of which I explored in Seminar 1. The universe is hypothetically expanding, and light is travelling at the same speed, so there's a constant 1-to-1, or c to c, slope of the light cone, and you can see that it curves around into the past, as I'll try to explain. The circumference of this expanding hypersphere is a graph of the present moment coordinates of observable space, that is, everything that is occurring simultaneously at our present moment. This is a universal now, which of course is not absolute, but relative in the sense that every observer has their own local position and velocity, so that at great distances our now completely diverges from that of other observers. And the result, as I'll explain, is that there is no definite antipodal point, and angular coordinates can continue past this point without repeating. For example, this trajectory of a high-speed particle has a separate local space axis, which is dramatically different from our own local simultaneity because of the high velocity of that particle. Time and space rotate into each other as a result of high velocity. So every trajectory, even yourself out walking the dog, is an independent time axis with your own space axis, which for that moment is universally shared only by you and your companion. Your universe at that moment is not absolute. It's purely local to yourself and to anything else that's moving with you at the same velocity. So this spherical looking model is in fact only relatively spherical with an indefinite antipodal point. It doesn't join up at the back. It's an infinite universe in principle, as real angular coordinates continue past that point and don't repeat, but it has a finite observable horizon. So this is a model of the view of everything that the observer could possibly see at this instant, as far out as we can see, including the microwave data that reveals what was happening only a few 100,000 years after the Big Bang, which is depicted at the center of this model. Huygens Principle states that every point on a wavefront is a source of spherical wavelets. The light from a star, for example, is a very large-scale spherical wavefront with an inverse square law deriving from a spherical surface area. But when you zoom in on a star's spherical wavefront on the scale of a planet such as the Earth, you find that the wavefront is only imperceptibly spherical and looks flat. Huygens' principle shows that in the close-up, that any wavefront, whether ideally flat or overtly spherical, can be thought of as a detail of spherical wavelets that mirror the large-scale spherical curvature at a microscopic level. So that's a remarkably self-similar structure that works to explain the whole range of macroscopic wave behaviors such as reflection, refraction, and diffraction. Huygens' wave theory of light was the first of its kind and was not accepted at the time. In fact, it was supplanted by the corpuscle theory of light due to Isaac Newton, which came out about 9 years later, in which light would be a particle presumably described by Newton's first law, that the velocity of light is a constant unless acted on by a net external force. Newton could not have known the mass or velocity of light, and he did not know what forces would act on it. But the otherwise successes of his theory meant that Huygens' wave theory was buried for more than a century. And it's instructive, I think, to wonder what might have happened if Huygens and Newton had got together and worked on a common theory. I don't actually know if they met or corresponded or even knew of each other's work, but we can now see that they were both right. If you tried to combine Huygens and Newton into one theory consistent with modern physics, it might look like this. Here I've redrawn Huygens' principle in 4 dimensions to represent the fact that the universe is at least 4-dimensional and is expanding. The observer is still internal to this picture and observes a moving particle at velocity v in the same dimensions on this plane volume, which is the sum of these 3 spherical wavelets. Now, by 3 spherical, I actually mean a 4-dimensional sphere whose surface is a volume. This idea comes from non-Euclidean geometries where the only properties of interest occur in the volume of the brane, or the membrane as it's called, the surface or volume of observable physical effects. And you can effectively say that the interior of such a sphere does not exist. So, if you have a 3-sphere expanding at light speed, everything of interest is on the surface volume of that sphere, and so everything is moving at light speed. This could mean that every particle is in fact moving at Huygens wave speed, and the Newtonian relative velocities that we observe are projections of light speed into our reference frame. The simplest construction you can use to do this is a simple trigonometry. The sine function, which as I pointed out in Seminar 1, is both significant and problematic in modern cosmology. If you project a light speed motion using a sine function representing the relative velocity, then the essential partner of sine, the cosine function, exactly reproduces the contraction effect or Lorentz-Fitzgerald gamma function that Einstein used to remake all of our notions of space and time. This is the actual special relativistic contraction dilation effect here in its correct form, even by this simple method. In this figure, I'm showing that a moving body with a characteristic proper length L and frequency f projected as a relative velocity into our reference frame by a sine function is also contracted in length and dilated in frequency by the cosine function, which is mathematically an exact Lorentz-Fitzgerald effect. This derivation, which will be ludicrously easy to anyone with a background in relativistic physics, is right here in just 2 lines. And this is the simplest derivation of the special relativistic contraction effect you will ever see. Usually it takes pages of work, and I can attribute this to a science writer and educator, Louis Epstein, who first saw this simplification and published it as a myth. He called it a myth for educational purposes. But Epstein did not associate it with a cosmology or with a 4-dimensional expansion of this type, and he did not associate it with Huygens Principle. This image by Paul Nylander seems to capture a lot of what I'm trying to describe. If we picture the expanding universe as a system of co-expanding bubbles of some sort, which are actually smaller with distance because the universe was smaller in the past time when we observe it at those distances, then you can imagine yourself, the observer, looking out at moving massive bodies or particles that project into our reality with space-time warping effects that are exactly as Einstein explained in both special and general relativistic terms. You just have to remember that the surface of these bubbles is a volume which relates to the volume around the observer at those distances. The distorted reflections in this image are, of course, they're calculated using software that would understand Huygens Principle. So seeing how effective this idea is, not to mention how historically significant, I set about trying to show mathematically the transformations that lead to metrics of general relativity. This figure combines both a conventional space-time diagram and a slightly modified Epstein diagram. A conventional, even Galilean trajectory is just a line indicating the slope of a particle's motion of space in time, so you get this angle theta and the conventional projection of a velocity as a tangent function. The distances are all distances in a common time, such as a characteristic vibration period at light speed or the particle's velocity. This is just the effect of multiplying a time value by the gamma function. So with velocity as a variable, you get these hyperbolic trigonometric spacetime curvatures, often described by analogy to circles in hyperbolic spacetime. But if you divide by the gamma function, the characteristic time period is contracted onto a Euclidean circle, which has this sine and cosine of a revised angle phi. This is significant as it revises the range of the time and the space axes. For instance, particle velocities are increasing dilation and contraction effects such that at light speed, the space and time axes have completely switched places and rotated through a right angle. Now, this surprising result has a very simple geometry relating exactly to Epstein's construction and hence to Huygens Principle. In this next slide, I want to show that you can derive the same result just from the proposed not just Huygens Principle, but a Huygens-Newton principle, using only the simple trigonometry that Huygens and Newton would have known. You get the same contraction and dilation effects as in special relativity, which can be projected in different directions for different comparisons, and the physical mass of a body is important in defining its physics as a limiting projection of this hypergeometry. Compared to light, which is massless, the physical dimensions and relative evolution of the body are determined by electromagnetic and gravitational effects with independent Huygens wavelets at the leading and the tailing ends of a body. We can regard these now as theoretical constructs with necessary quantum corrections. So, still looking for an explanatory cosmology, I set up a system of differential equations representing an expansion at equal radiation velocity. To show you how I did that in steps consistent with special relativity, In the lower frame there's a conventional Minkowski diagram, and in the upper there's a Huygens-Newton diagram with the corresponding angles and functions. I've joined the two trajectories, and I've shown corresponding one-to-one light cones in each frame. And it's interesting that in this diagram the comparison again just shows an additional contraction by gamma. So the values of inverse gamma and inverse gamma squared are both legible as Euclidean geometry within this picture. This next slide is the step up to a large-scale cosmological curvature. We can allow a flat Euclidean geometry to assume spherical curvatures, but now with the curvature there's a polar geometry with angular coordinates. There's two differential equations as descriptions of the light cone. The radius of the wavefront is increasing at the speed of light, and light is radiating in 3 dimensions only on the surface volume, also at the speed of light. If we call the radius s, it identifies well with the distance that light can travel in the age of the universe, s equals ct naught. So this picture is around 14 billion light years in radius. The lower frame still shows a slightly earlier time at a smaller radius that we can associate with a cosmological scale factor, just as the ratio of past to present s, or proper distances, are in 3 space. At the scale of this diagram we can see some important cosmological effects. Firstly, that the angular velocity must decrease even as the expansion and radiation velocities are constant, which relates to the Hubble value as shown in Seminar 1. And secondly, that the Huygens wavelets must diverge, requiring for continuity reasons that they stretch, which gives rise to a cosmological redshift. So these two hypotheses about light speed provide two differential equations, which I show as equations 1 and 2. In the next page I'll show the math steps that lead to these two polar spirals. The first one a forward view and blue shifted, and the other one a red shifted view in the other direction. And you can see here that the solutions do look like they work correctly because the slope of the light cone is always 1-to-1. At any point on this curvature, the light cone hits the radius at an angle of 45 degrees. And I'll just note here that these results have a lot in common with standard model cosmology. There are several different ways of plotting a light cone, the upper one here showing a low density universe, and the lower one with hyperbolic curvatures that reduce the cosmological curvatures to straight lines. In all 3 plots, the universe can be said to be infinite and unlimited in recession velocity, but with a visible horizon at the Hubble radius and the speed of light. Okay, if I do this on something like a blackboard, these two light-valued DEs, as in any particular order, an angular radiation coordinate velocity, recognizable from Seminar 1, and a radiation expansion velocity, and we just divide one by the other to combine the two effects into a single differential equation which is just equal to the Hubble radius. That equation can be rearranged to solve for the radius as a function of angular coordinate, as seen from the observer's internal view, out along the light cone. This inverse differential of the Hubble radius leads to a logarithmic integral, with the present Hubble radius as a boundary condition. Knowing anything about the exponential function, this looks like it should do the J-curve effect of growth into the future, or inversely shrinking into the past. But because of the introduced Huygens polar coordinates, the result is a system of exponential or logarithmic spirals, being geometrically similar to a nautilus shell growth spiral. This picture is actually one step further than I've just derived to show the effect of a proper velocity with the Huygens-Newton relativistic effect, to round out the story and to bring us back to slide 1 to show you where that came from. If you want to see how those next steps work, you're welcome to stay for the full 50 minutes, but I'll offer a question break here, and people can shoot through at the end of that if they need to. Okay, so how do we work out ordinary distances in this flat spherical cosmology? We have to define visible distances in 3 dimensions, the only directions that astronomical signals can travel in. In polar coordinates, you can easily define a distance as an arc length, just a segment of the circumference that we defined as the present 3 space, just by multiplying the radius by an angle, or an element of an angle. So dx equals s d psi is a universal arc length law. And you can define your radius s as however it varies in your model and add it up. So we've got this exponential function, which has the useful property that integrates as the same function, just with a minus sign that comes out of the index. But the limits are from 0 to a coordinate, any distance out to infinity, so the definite integral of distance becomes a difference between the Hubble radius in the present and at any time in the past. Then, when you substitute in the expansion equation, equation 1 in fact, which is the Hubble radius expanding at the speed of light, you get a simple difference in light travel times, c delta t, which is the standard null metric, distance at light speed, the most basic distance along a light cone. So that checks out as the natural correct answer for a visible distance, and it has this exponential law built right into it. Then how fast is that distance increasing, as indicated by the expansion of the universe? Well, having defined an integral distance of arc lengths, if we differentiate it using a chain rule that is as general as it can be, and recognizing that we can keep it simple by assuming co-moving coordinates, that is, the angular coordinate doesn't change between two cosmic distances, such as our galaxy and a distant galaxy, then it simply reduces to this dx by ds, where ds by dt is the speed of light, again from equation 1, and it leaves us with a recession velocity which is proportional to distance and inversely proportional to time. That's as near as you like to the standard model Hubble factor, which is a time-varying proportionality and a constant throughout the present observable universe. The standard model or concordance lambda CDM model has that same factor as 0.96 divided by the age of the universe, where this is just 1 divided by the age of the universe. So I need to show how the standard model redshift derives from this exponential model, and we can do it again by considering the light cone as the locus of all events that are presently visible to an observer. So say we're looking at a distant galaxy, and the light we see is received from billions of years ago. But the light that we see has to be continuous in the sense of a train of light waves that connect up peak to peak for at least some period of observation. So a photon that's released at that time and a small period of time later, such as the period of production of that wave by an atom, both of those photons being released at that time must remain continuous as they propagate through space-time until they eventually reach us here at the present as a continuous stream of light from that particular event. So this diagram shows the exponential curvature of the light cone at those two successive instants, and you can see that the time difference between those two approximately parallel exponential functions gradually diverges, with each photon in the continuous series of photons radiating and expanding at constant velocity. If the photons themselves retained the same wavelengths, then they would no longer connect up with other photons in this series. You can see that they're actually diverging from this particular interaction. In other words, this diagram is inaccurate insofar as the wavelengths can't stay the same and remain continuous. To remain continuous, they must stretch to some degree, and the amount of stretch is exactly that visible divergence. It's a gap in time between successive light waves as they occurred when they were produced and as they are seen in the present some billions of years later. Another way of looking at it is that for any short time interval here at the observer, the difference between t0 and t0 prime, say, there is a smaller time interval at the distance of the galaxy that we are observing. And that's in spite of the fact that that galaxy is expanding at the same rate as us, and at that time it still was expanding at the same rate as us, the speed of light. From our point of view, that galaxy would seem to be evolving more slowly than ours because less time passes there for any time that we measure here. And in fact, the visible time dilation would be in the same proportion as the visible dilation of the wavelength, pretty much exactly as we understand the cosmological redshift. We can also look at the special relativistic effects of proper motion on redshift, that is, how we evaluate the relativistic Doppler effect at great distances assuming relative velocities, which can be as small as galactic peculiar velocities around 100 kilometers per second. The exponential light cone solution, derived for the speed of light, can be repeated for small velocities. And in the same steps, we can integrate by substituting v instead of c and integrate in the same way as before. And what we get is a forward predictive polar logarithmic spiral with the special relativistic beta function v over c in the denominator of the index. So this trajectory spirals upwards at a constant slope of c over v, which conforms to the vertical time axis when v is 0. This second last slide shows that these exponential spirals, as this derivation has defined them, are in fact special relativistic without further correction. If we consider this interaction between our galaxy G, here at time 1, and some distant galaxy, call it H, a particle from our galaxy travels at high velocity over several billion years and arrives at H at this point, but we can consider its distance at that starting moment along the x-axis and consider how far is that and how does it compare to special relativity. So we're integrating small elements d of a distance x from G1 to H along x, and again we're defining 3 space as small angular projections on coordinate elements d psi. The integral is again straightforward. The beta factor must appear in the coefficient denominator, so you're multiplying by c over v. But the initial radius S1, is c times t1, so the c multiplies into the factor and you get c squared on v by the time difference on the x-axis. And it's not hard to show by rearranging these terms that the Lorentz transformations are a direct consequence of this spiral geometry. In fact, all it takes is a gamma factor introduced on both sides of the equation, which then reduces to an exact transformation familiar from relativity. The result, long story short, is a model of special relativistic redshift with a version of the cosmological scale factor that has an inverse relativistic Doppler effect in the index. This is only a tiny correction for any galactic proper velocity, but it is just enough to explain why the CMB has such a large redshift dipole, indicating an apparently large peculiar motion of our galaxy, much larger than any typical intergalactic motions that we can directly measure. It's been a mystery for the last 30 years or so, but it may be resolved by the essentially refractive effect of this Huygens model, which does produce that degree of redshift even for a normal intergalactic motion. I'll take questions on it now, and perhaps I'll see you again in Seminar 3.